Hello everyone again and welcome to the Daijo Merit channel, where we're going to dive into various interesting examples mainly in physics, which is focusing on the magnetic field strength of a specific particle. Now in this particular video there is a specific question which states, in a situation like a helical particle, the charged particle is a proton. Now we know that a proton, which we're going to represent as a blue circle right here, is actually having a quantity of charge to be pretty much the same as the quantity of charge of an electron, which is 1.6 times 10 to the negative 19 coulomb per charge. And this actually has a mass which is pretty much 2,000 times more than that of an electron's mass, which in this case for the mass of a proton is 1.69 times 10 to the negative 27 kilograms. And in here this is actually subjected to a specific magnetic field with around this particular strength of 0.5 Tesla, and this is actually directed on the x-axis. So in this case, once you're actually able to figure out that it's more about coordinates, then we actually draw our sketch of a coordinate where this is actually in the 3 dimensions, and we put this as our z, and in here we label this to be our y, and this is our x axis. So in this case they are all positives and the other lines are the negative values. And now we know that the magnetic field is actually positioned in here to be on the x-axis. So pretty much what we actually imply is that it's going to be leaning towards this particular direction right here. So we have this arrow which is parallel to the x-axis for the magnetic field strength. And also we know that the position of the proton has a velocity which is in the 3 dimensions components, where on the x-axis the velocity is around 1.50 times 10 to the 5 meter per second, and we have the y-axis to be equals to 0 velocity, and our z-axis the velocity is around 2.0 times 10 to the 5 meter per second. So in this case, when we are putting our particle, we expect our particle to be somewhere around here with this particular position of our x-axis to be positioned right here with that velocity. We'll label this to be I for the unit vector on the x-axis, and then the unit vector on the z-axis in this case is labeled as k, and it has that specific value of 2.0. So our net, I would say, vector is actually positioned in this particular direction along the xz plane, not including the y-axis. So in this case what we're going to figure out is pretty much at the beginning, which is at time equals to 0, what is the force, which is a, and what is the acceleration based on the force of that particular particle, which is our proton, in that particular magnetic field, which is B. So first off, we need to take into consideration is that to obtain the maximum force, which I'm going to put as condition 1, to get the maximum force we need our coordinates right here, which is our z coordinate, which I'm going to represent as k unit vector, to be perpendicular to another vector which we're going to call our x coordinate, which is merely the magnetic field. So in this case, since we're going to be playing around with velocity, because we are dealing with magnetic field forces and that of the magnetic field, we expect that the velocity to be perpendicular to the unit vector of the magnetic field. That is for the first condition. And the second condition here is that if we want to get a zero force magnetic field, we need to have our component on the velocity to be parallel to that of the magnetic field in that particular space. So in this case, if you have two vectors that are parallel to each other, then we get our force to be equal to 0. So once we're able to figure out these two particular conditions, then we can apply it to this particular question right above right here. So in this case, once we're able to figure this out, we go to our A and we write down our magnetic field force to be equals to as follows. We have the quantity of charge, which is the absolute value, multiplied by the cross product of the velocity and that of the magnetic field strength. And in this case, since both vectors here, we're going to consider the x and y coordinates and the z coordinates. We will going to go ahead and put those coordinates in there with respect to the unit vectors in there. So the y, since y is j unit vector, plus the v z, and in this case we have the k to be the unit vector in that particular component. Magnetic field on the x with the unit vector plus that of the magnetic field on the y, which in this case is the unit vector j, and that of the magnetic field on the z, and what we get in this particular case is the unit vector on the z to be k. Then we actually apply our conditions to the following. In here we don't have our y coordinate for the velocity, so that equals to 0 in this case, and we don't have any magnetic field on the y-axis, and likewise that on the z-axis, I believe, based on this particular question. So in this case, our z-axis here doesn't have any magnetic field strength. It's only on the x-axis for the magnetic field, and for the velocity we have our x velocity and the z velocity. So in this case, once we rewrite those, in this case we have our quantity of charge, and that is multiplied by the velocity on the x with our unit vector plus the velocity on the z with the unit vector k, and is a cross product with that of the magnetic field on only the x-axis. So this is where we actually combine the first condition, which is what we have right here, and the second condition right here. So what we notice in this case, in this expression, is that since we have the x-axis right here, and we notice that x-axis is combined with that of the x-axis with the velocity, it means that since the x-axis is all on the same line, it means that they are parallel to each other. So in this case, the combination of the vector here I and the unit vector I means that they are parallel to each other, and as a result, the resulting vector is actually equals to 0. So that is actually taken away, but here we're actually going to add in the combination of our z velocity with that of this magnetic field x. So in this case, since the z here is perpendicular to the x-axis, so it means that we're getting the maximum product, which is now on the y-axis using the right hand rule. So in this case, since it's y, we're going to be using our unit vector to be j. Once we're able to analyze that, we come to a result which is as follows. We have the force of magnetic field to be equals to the product of the quantity of charge multiplied by the velocity on the z axis with that of our days multiplied by that of our magnetic field on the x-axis. So the combination of our unit vector of k and I gives j, and as a result we get our result to be velocity on the z multiplied by the magnetic field on the x with our unit vector j, which is on the y-axis. So if you put down your values, 1.6 times 10 to the negative 19 coulomb multiplied by our velocity, which in this case on the z-axis is at the top, which is 2.0 times 10 to the 5 meter per second, multiplied by the magnetic field strength, which is 0.5 Tesla, and this is on the y-axis. We get our resulting magnetic field to be 1.6 times 10 to the negative 14 newtons, and this is actually on the y-axis with a unit vector j. So once we're able to figure out the magnetic field force, then our next question here is to determine the acceleration. And to determine the acceleration, we do know that the net force is actually equals to the mass of a proton, which is in focus, multiplied by the acceleration, and in this case is equal to the force of the net magnetic field. So in this case, what we know in here is that the mass of proton in question is 1.7 times 10 to the negative 27 kilograms, and we're determining the acceleration, and we know our force to be equals to, let's go the other way around, 1.6 times 10 to the negative 14 newtons. That means you divide both sides by the mass, kilograms divided by 1.69 times 10 to the negative 27 kilograms. So the mass cancels out the mass, and our acceleration of that particular electron at time 0 is our 9.58 times 10 to the 12 meter per second square. So that is about it for determining the acceleration based on the magnetic force acting on a specific proton in a magnetic field. All the same, thanks for following me through this, truly appreciate it. Hit the comment down below, let me hear your thought about anything I missed or any other alternative solution to the same problem in here. All the same, stay smart and believe in yourselves.